portion of this video is brought to you by Incogni. With the ever-growing demand for electrifying everything, we need more sustainable batteries. Lithium-ion devices are cost-effective, but rely on lithium, graphite, and other materials whose sourcing has significant environmental and social impacts. And one possible solution is being developed where wood is used to replace these materials with a bio-based alternative. So would work, or is it just dead wood? It's a lot of wood. I'm Matt Ferrell. Welcome to Undecided. I've said it before and I'll say it again, but it feels like there's some crazy new energy storage breakthrough happening every single week. And this one might start setting off alarm bells for you when you hear that some energy storage developers are incorporating wood byproducts into their battery design. It raises a lot of questions. Is this really sustainable? How well does it work? And probably the biggest one, why? Now, to understand the value of bio-based batteries, we should first look at why lithium-ion batteries might not be as good of a solution as you think as a long-term solution. It'll help to illustrate why these bio-based batteries might be a good indicator of where battery technology is heading. Lithium-ion batteries are ubiquitous in today's world. You can find them in smartphones, cars, or even large-scale energy storage systems. Compared to the old-fashioned lead-acid batteries, lithium-ion devices recharge over 4 times faster, last 10 times longer, and store up to 10 times more energy per unit of volume. You can probably see why electronic devices have become smaller. Also, you can now drive your EV for a long time without stopping and wasting less time charging it up. There's no doubt about it. Lithium-ion devices make our high-tech life much easier and have opened doors to new technologies. But lithium-ion batteries are charged with sustainability violations. For instance, you typically get lithium by evaporating water out of massive ponds containing a salt solution known as brine. For each ton of lithium that you recover, you lose around 500,000 gallons of water. To put that in perspective, that would only be enough to make batteries for 1,000% of all the cell phones in the world. In Salar de Atacama, a salt flat hosting around 40% of lithium global reserves, extraction drinks up 65% of the Chilean region's water. That's not the worst of it though. Refining it to battery-grade lithium carbonate contaminates the few drops of leftover water with toxic metals such as antimony and arsenic, which means even less usable water for the indigenous people. On top of that, the manufacture of battery-grade lithium accounts for 40% of the device's carbon emissions. Lithium is not the only high-carbon ingredient of traditional batteries. As of today, the anode of lithium-ion batteries contains graphite, which is a carbon-based and carbon-intensive material. In a recent study, Minviro assessed the global warming impact of sourcing graphite in regions like Inner Mongolia, who rely on coal-based grids. The environmental consultancy's estimate was up to 1,000% higher compared to previous reports. Apart from releasing CO2 into the atmosphere, graphite mining and refining contaminates drinking water and crops with dust in China, where the Chinese company BTR takes around 75% of the natural graphite global demand. Aside from the supply chain issues, graphite-based anodes don't like to be in the cold. To be more specific, the charge they can hold drops quickly as the temperature goes below the freezing point. If you've ever driven an electric car in the cold weather, like I do, you know what I'm talking about. Now, previous research identified the flat orientation of graphite in the anode as the culprit of lithium-ion batteries' rapid discharge at sub-freezing temperatures. High temperatures aren't any better because they could potentially lead to the evaporation of flammable compounds contained in the electrolyte organic solution. As a result of this thermal runaway, the battery could get damaged or catch fire. And not to exaggerate the reports of lithium-ion battery fires, but it does happen. For instance, the batteries in the world's largest energy storage caught fire twice in 5 months. And that's where the wood battery comes into the picture. And yes, I do know, wood can burn too, but these might be more sustainable and less risky approaches to pursue. As mentioned earlier, graphite is not the optimal ingredient for a battery anode, which is why the Finnish company Stora Enso is providing the Swedish Northvolt battery manufacturer with a more sustainable raw material. This is called Lignode, as it's made of lignin, a carbon-rich polymer that makes up 25% of wood's structure. Second to cellulose, lignin is one of the most abundant renewable carbon sources on Earth. Stora Enso is sourcing lignin from sustainably grown forests in Nordic countries. And the result of this joint effort is a 100% EU-based growable battery supply chain, where Northvolt will take care of cell design, battery assembly, and scale-up. Now, swapping graphite with a local biocarbon in their battery anode, the company is aiming to reduce its production cost and carbon emissions, which sounds great, right? But how do you turn trees into a battery anode component? Now, before I get to that, I'd like to thank Incogni for sponsoring this portion of today's video. I've mentioned this before, but I signed up for a newsletter from a small online retailer, and after I did, I saw a major increase in the number of promotional emails I was receiving from companies I had never heard of. And that's because they sold my information to a data broker. I've also had my information leaked through data breaches at companies like Target, Sony, and others numerous times. I'm sure you've experienced it too. And Cogni can help you with this. We have the right to request that data brokers delete our information, but it takes a lot of time and effort. I signed up for Incogni, gave them the legal right to work on my behalf, and then they just sat back and relaxed. You'll see updates on your account for which data brokers they've sent legal requests to and which ones have complied. It couldn't be easier. I've been letting Incogni stay on top of this for me for quite a while now, and I'm really happy with the results. I've noticed a big difference. And if you want to take back some of the control around who has access to your personal information, give Incogni a try. The first 100 people to use Undecided at the link below will get 20% off Incogni. Thanks to Incogni and to all of you for supporting the channel. Now back to how you turn trees into a battery anode. You probably know that wood is a standard feedstock for producing paper. What you might not know is that lignin is one of papermaking's byproducts. Typically, lignin ends up in an incinerator to generate energy. Instead, Stora Enso upcycles it into a hard carbon powder, also known as char. This is a crucial step as it turns an insulator like lignin into a conductor like carbon. The charred lignin is then pressed into an electrode sheet that can be assembled with other cell components. But is it really green? Will it mean more forests being cut down? Well, thanks to this circular approach, the biomaterial supplier won't need to cut down additional trees. Apart from being more climate friendly than graphite, the manufacture of lignin-based anode would be easier to scale. Just think that European producers could tap into the 17 million tons of lignin generated every single year as a byproduct of the paper industry, which are currently not being used. Now in 2021, the Finnish company launched a pilot plant to start producing their Lignode. They strategically built it on the same site as their existing biorefinery, which is extracting 50,000 tons of lignin from pulp every single year. Other than electric mobility, their lignin-based anode is suitable for consumer electronics and grid-scale stationary energy storage. As claimed by Stora Enso, Lignode would allow for faster charging compared to graphite-based anodes. As reported in their white paper, their material has more disordered and open structure compared to graphite, which is arranged in regularly spaced layers. This framework is more accessible by lithium ions, which speeds up the charging process. Now, while they haven't provided any evidence for that yet, their claim might be solid as wood. Previous studies showed that graphite interacts with the electrolyte solution during the charging process. This leads to the formation of a solid layer over the anode surface, which slows down the movement of lithium ions, which limits the charging rate of the battery. Now, for this reason, researchers have turned to bio-based carbon sources to replace graphite in the battery anode. Last year, a Japanese group harnessed a biopolymer to make a battery anode and achieved a shorter charging time compared to those obtained using a graphite. Stora Enso also touts that the Lignode structure improves battery performance at temperatures that are below freezing. Once again, this seems to be plausible. As mentioned earlier, the poor low-temperature endurance of lithium-ion batteries was associated with the graphite-leveled surface. Recently, Chinese scientists boosted the durability of lithium-ion devices at temperatures as low as -31 degrees Fahrenheit or about -35 degrees Celsius by replacing its graphitic anode with one made of carbon nanospheres having a bumpy surface. Stora Enso isn't alone here. Rather than just replacing the graphite-made anode, Ligna Energy has come up with an organic recipe for a whole battery. With lignin, water, and natural polymers as main ingredients, their formula has a bio-based content of up to 80%. Just like Stora Enso, this Swedish startup is recovering lignin from paper manufacturing side streams. They then mix lignin with carbon through a process called dry ball milling. The result of this organic cocktail is a conducting nanocomposite that's fed into a printing press to make an anode sheet. But Ligna Energy introduced another key innovation, an electrolyte solution made of water and potassium polyacrylate, which is a super absorbent polymer used for baby diapers. Now, I don't know about you, but I've never heard of babies catching fire because of a dirty nappy. So I guess it's safe to assume that potassium polyacrylate-based electrolytes aren't flammable. Now, I know this sounds too good to be true, but dirty diapers aside, but when presenting their creation at COP26 in 2021, Ligna Energy won the Startup for Climate Innovation Award. This is one of Europe's biggest energy innovation challenges where green tech, energy, and climate action experts shortlist the best ideas for promoting a transition to clean power. Now, while Stora Enso and Ligna Energy are leading the way to try to bring wood-based batteries to the market, a team of Swiss researchers printed a 100% biodegradable battery on a piece of paper. How does that even work? Well, scientists formulated two inks, one containing graphite for the air cathode and a zinc-based one for the anode. They then stencil printed one ink on the front and the other on the back of the paper strip that acted as a separator. To make this metal air battery work, you just need to add a pinch of table salt and a couple of drops of water onto the sheet. And when doing that, you create the electrolyte solution that triggers redox reactions and allows electrons to travel between the two electrodes. In their lab experiment, researchers harnessed a 2-cell battery to power an LCD alarm clock. Typical Swiss. Anyway, that's still just a lab experiment, but a cool example to show what's possible. Now, all these inventions are electrifying, but will they perform well enough to switch off lithium-ion batteries for good? A low energy density might restrict their use in some applications, but we'll get to that in a minute. Clearly, wet bio-waste sounds like a way safer and greener battery raw material compared to lithium and graphite. But are these bio-batteries worth a shot from an economic standpoint? Now, none of the creators have disclosed any comprehensive estimates yet. However, based on one of Ligna Energy's scientific advisors, all the materials used in their battery cost less than $1 per kilogram. If we consider raw lignin, this quote seems to be correct. According to some estimates, recovering lignin through ultrafiltration of pulp would only cost about 6 cents per kilogram. However, this figure doesn't factor in the cost of upcycling the recovered lignin into a material suitable for battery anodes, like Stora Enso's Lignode, for instance. And just for comparison, you would need to spend $2 for making 1 kilogram of synthetic battery-grade graphite. As with any other technology, scaling up will lower the production cost. The question is, will these technologies get to the market? Now, obviously, it's hard to say for printable batteries as the ink isn't even dry, it's still in the lab, though the lead researcher hopes to turn them into real products within 5 years. Now, that seems optimistic to me, but how about the other two solutions? Well, as it stands, Stora Enso's Lignode is ahead of the biocharging race. We've already mentioned that the Finnish company Trial Line has been churning out lignin-based anodes over the last year. Last October, the company went beyond that by signing a letter of intent with Beyonder, a Norwegian energy storage developer. As part of this agreement, the pair committed to optimize Lignode properties and fast-track its scale-up. On top of that, Stora Enso can also rely on Northvolt's existing gigafactory infrastructure in Sweden. Back in 2017, Stora Enso's head of innovation predicted that the material might reach commercial production by 2027, and they're still on that track. Based on their last year forecast, the company pilot could reach full scale by 2025. As for Ligna Energy, last March the startup raised $1.4 million. Now, while there's still no clear timelines on when their grid-scale storage application will turn into a real-world use case, they've just released a rechargeable unit for IoT devices, such as temperature and moisture sensors used in smart buildings. But how do they stack up against traditional devices that are available right now? In terms of energy density, Ligna Energy battery would only be able to store about 40 watt-hours per kilogram. And when you compare it to lithium-ion batteries, that's nearly 7 times lower. To bypass this obstacle, the startup is focusing on stationary applications where heavy weight isn't an issue. And while Stora Enso hasn't revealed any exact figure yet, they expect the lithium-ion battery featuring their Lignode to be less energy dense than the benchmark. Now, other than packing in as much energy as possible in a smaller and lighter container, we should extend our battery's lifespan. But what does that mean from real life? For example, a lithium-ion battery in a typical electric car retains 80% of its charging capacity after 2,000 cycles. Ligna Energy heralds that their battery could push this to 5,000 cycles. Just like for energy density, Stora Enso hasn't provided a specific value, but they claim that swapping the graphite anode to their Lignode will increase lithium-ion batteries' cycling stability. So obviously, with the dramatically lower energy density, this isn't a solution for electric vehicles, but that doesn't really matter. Reusing existing waste streams for a material supply has big potential economic upsides. And just with all the technologies that I cover on the channel, there's no silver bullet. It's all about picking the right tool for the right job. If these batteries are cheaper to produce and buy, they'll find a market, most likely in stationary energy storage or small IoT devices at first. Now, using bio-based materials instead of graphite and lithium would certainly improve the sustainability and safety of our batteries. It can also help give more countries and states a supply chain that they control themselves. Stora Enso and Ligna Energy are on the right track for bringing their products to the market. However, let's see the wood for the trees. Some of the claims made by these technologies are only on paper, and developers need time to iron the wooden kinks out. Regardless of how this develops, it's this type of research and thinking that shows us where batteries and energy storage are potentially heading. So you still undecided? Do you think looking for alternative bio-based solutions is where batteries are heading? Jump in the comments and let me know. And be sure to check out my follow-up podcast, Still to be Determined, where we'll be discussing some of your feedback. If you liked this video, be sure to check out one of the videos over here. And thanks to all of my patrons for your continued support. And welcome to new Supporter Plus members, Any Last Wishes, John Hoger, JH, and William Odell. And thanks to all of you for watching. This is the last video for the year, so have a great holiday season, and I'll see you in the new year.